Genetic optimization algorithms optimization problems are at the heart of modern computing, driving advancements from machine learning to logistics. Among various approaches, genetic optimization algorithms stand out as powerful tools inspired by natural evolution. These algorithms mimic biological processes such as selection, mutation, and crossover to solve complex optimization challenges. In recent years, the demand for efficient solutions has surged due to increasing computational complexity across industries. Genetic algorithms offer robust methods that adapt well to dynamic environments, making them indispensable in fields ranging from engineering design to financial modeling. The foundations of genetic algorithms at their core, genetic algorithms operate based on principles derived from Darwinian theory. They begin with an initial population of potential solutions encoded as chromosomes within a defined search space. This population evolves over generations through iterative application of three primary operations: selection, crossover, and mutation. Selection ensures better performing individuals have higher chances of reproducing, while crossover combines traits between pairs to generate new offspring. Mutation introduces random variations into the genome, preventing premature convergence towards local optima rather than global ones. Together, these mechanisms enable exploration of vast solution spaces efficiently. Selection, fitness evaluation determines which candidates get selected for reproduction, favoring those with superior performance metrics. Crossover, by exchanging segments between two parent chromosomes, novel combinations emerge that might yield improved results. Mutation, random alterations maintain diversity within populations, ensuring continued adaptation even under changing conditions. Applications across industries from manufacturing systems to investment portfolios, genetic algorithms find applications where traditional mathematical techniques fall short. Their ability to handle nonlinear relationships makes them ideal for real-world scenarios involving numerous variables. For instance, aerospace engineers use GA-based simulations to optimize aircraft designs without relying solely on expensive physical prototypes. Similarly, portfolio managers apply similar logic when balancing risk versus return trade-offs among assets. Different sectors leverage GAs uniquely. However, common themes include multi-objective optimization tasks requiring simultaneous consideration of competing priorities. Sector-specific examples: agricultural planners utilize these algorithms to determine optimal planting patterns considering soil quality, weather forecasts, and market demands simultaneously. Such integrated decision-making significantly improves crop yields compared to manual planning efforts alone. Urban traffic management benefits too. By analyzing historical data along with current sensor inputs, cities can implement adaptive signal timing strategies that reduce congestion during peak hours effectively. Healthcare professionals employ GA-driven models for personalized treatment plans tailored specifically around patient characteristics, including age demographics, pre-existing medical history factors, etc., enhancing therapeutic outcomes dramatically. Evolving techniques within GA frameworks. Ongoing research continues refining existing methodologies within genetic algorithm paradigms. Innovations such as hybridization with other meta-heuristic approaches enhance overall effectiveness considerably. Newer variants incorporate elements from swarm intelligence, allowing collaborative behavior among agent-like entities operating independently yet contributing collectively toward achieving shared goals. Additionally, parameter tuning remains crucial since improper settings could lead either excessive randomness diminishing useful information retention or overly restrictive constraints stifling innovation opportunities entirely. Challenges faced during implementation. Despite promising capabilities, implementing effective GA systems presents several hurdles worth addressing thoroughly beforehand. Properly defining objective functions, accurately reflecting desired end states proves challenging, especially amid ambiguous requirements contexts. Data pre-processing stages require careful handling lest skewed distributions distort final outputs erroneously. Ensuring adequate representation across diverse subpopulations also becomes essential to avoid biases creeping into decisions made later downline. Moreover, Interpreting results obtained via stochastic procedures poses difficulties because, unlike deterministic methods providing clear-cut answers, probabilistic nature necessitates statistical analysis frameworks instead. Performance metrics evaluation criteria to assess how well any given implementation performs against benchmark standards requires establishing quantifiable measures aligned closely with intended purposes. Common indicators include convergence speed, accuracy levels achieved post-processing phases, resource utilization efficiency ratios measured accordingly. Comparative studies often involve running identical test cases using different configurations, then comparing resultant scores across multiple runs consistently repeated under controlled experimental setups. Such rigorous assessments help identify strengths/weaknesses inherent within particular implementations, guiding future development directions appropriately guided, thereby improving reliability assurances progressively over time periods. Considered acceptable industry norms today. Finding optimal parameters through tuning strategies. Selecting appropriate values for critical parameters plays pivotal roles determining success rates associated with each run executed sequentially following setup completion steps outlined. Previously described earlier sections above here. Parameter ranges need defining carefully, taking into account domain knowledge available regarding typical acceptable thresholds, applicable generally accepted practices followed widely recognized experts active currently working related areas extensively. Tuning methods vary depending upon problem specifics encountered during execution cycles undertaken repeatedly until satisfactory results observed meeting predefined criteria established initially before commencing actual trial sessions. Commenced subsequently thereafter. Future directions and research opportunities. Emerging technologies promise further enhancements capable transforming present limitations into advantages beneficially affecting broader applicability domains previously thought unreachable, utilizing conventional means exclusively employed hitherto thus far. Advancements in parallel processing architectures combined with cloud computing infrastructures open up possibilities enabling distributed evolutionary computations scaled horizontally according to workload intensities experienced. Dynamically fluctuating demand curves characteristic many contemporary business operations nowadays. Furthermore, integrating deep reinforcement learning concepts alongside classical GA structures may yield next-generation intelligent systems able autonomously adapting themselves, continuously optimizing objectives pursued relentlessly without human intervention required whatsoever. Conclusion: genetic optimization algorithms represent versatile instruments adeptly tackling multifaceted issues prevalent throughout technological landscape today. Their flexibility allows customization suited precisely individual needs irrespective varying degrees complexities involved therein. By embracing continuous improvement philosophies centered around iterative refinement processes embedded inherently within GA framework itself, practitioners stand poised leveraging full potential offered by these remarkable techniques, advancing frontiers science technology ever more rapidly than achievable otherwise.